Alright everybody, welcome to week 5, and this time we're going to be covering chapter 4, routing concepts. Alright, so first let's talk about networks and the characteristics that they have. First one is topology. Now when they're talking about the topology, it could come in two forms. They can either be talking about the physical topology or the logical topology. Physical topology is how your network is laid out. Is it laid out in a circle? Is it laid out in a square, a star, that kind of thing. And then logical topology is how the data moves. What does the data move through? What's the path of the data? All right, then they talk about speed. Your ports on your switches, your NIC cards, they all have different speeds. 100 megabits, 1000 megabits, 10 gigabits, you have fiber, things like that. So all that has to be taken into consideration, especially when you think about what happens when you've got a 24 port switch and 20 users are connected to there at 100 megabits per second. So now you've got 20 times 100 data going through that switch, and then it has to go to the next switch. So if you've only got a 100 megabit port connecting that switch to the next hop, obviously that's going to reduce everybody's speed down greatly. All right, and then cost. What do these things cost? Obviously, networking equipment is not free. The more robust equipment is more expensive. We all have finite budgets that we have to work into. All right, security. How secure is this device? How secure is this operating system? We can't be running Windows XP anymore because there's no security patches, things like that. All right, availability. How available is the stuff? There are some, smaller hardware vendors that you can have a hard time finding parts. Things like Juniper and Cisco, are pretty popular, and finding parts is relatively easy. Scalability. How does your network scale? And when we say scalability, what we're talking about is the ability of your network to grow without having to redesign it or add a bunch of hardware to it. Like for example, when we bought a phone system, we had 200 users, so we made sure that we had 250 ports on the phone system so that we could grow 50 more users without having to add new hardware to the phone system. So that's like scalability. All right, and then reliability. How reliable is the equipment? Sadly, if you have a Microsoft Windows server, having to reboot it is a normal process. Where having a Cisco router in a closet for 5 years without having to be rebooted is totally normal. So, how reliable is the equipment? All right, so routers. When we're talking about routers are really, they're just computers in a kind of a different form. They have a CPU, they have an operating system, they have RAM, they have non-volatile RAM, which kind of takes the place of the BIOS chip. So they have everything that our regular PC has. The major difference is, your PC has a hard drive that stores information, where the router has a flash card. Other than that, they all have the same parts. So to see what kind of parts and stuff are in your router, the first thing you want to do is go to privilege mode and do the show version command. So when you do show ver, it looks like this, and it'll give you all kinds of information. First one, here's the version of the iOS software. Remember, Cisco calls their operating system the iOS, so Internet Networking Operating System. So here's the version. So this is version 12.2. Blah blah blah. And then you'll find what's the name of the bootstrap version, how much memory it has. Now when you go into memory, it's a little bit different. So this is the regular RAM. So they give you two numbers. You have to add these two numbers together to get the total amount of RAM. The first number is how much is free. The second number is how much is being used. Again, model of the processor. Now remember, there are three types of memory in the router. There's regular RAM. Then there's NVRAM, which kind of works like the BIOS chip. It has power going to it even when you shut the router off. And NVRAM right there. So 125 kilobytes of non-volatile memory. And then it has flash memory. So here, 81, 92 kilobytes of flash memory. So remember, your router, the iOS and the files that go on your router are really relatively small. So it doesn't really need a hard drive. A flash card is all it needs. And most routers, typically a 32 meg flash card will house everything it needs. All right, so Again, the show version command pretty much gives you all the information on the router as far as the hardware goes. What version of the iOS, what version of the Bootstrap program, what version of the processor, how much RAM, how much memory. Now, one other thing that I like to point out is the configuration register that's always listed at the bottom of the show version command. The configuration register it's almost like the jumpers on a PC. You know how you can pull a jumper off and then it'll do this. Back in the old days when you tried to make it boot from CD first, you actually had to move a jumper. That's really what this configuration register does. So if I do it 2102, it means, hey, do normal operation. So the router boots up, the Bootstrap program then points to the flash card for the iOS. iOS loads. The iOS then goes to the start file in NVRAM, and if there's no startup file, then it just puts a blank file into the running configuration, the regular RAM, and says, hey, do you want to do the auto configuration? But if there is a file in the startup in the NVRAM, it loads that file into the regular RAM. So here, if I change this value to 2142, then the router skips the startup file. So again, the startup process, the router powers up, does a power on self-test, loads the iOS, then goes to the NVRAM and grabs the startup config, and then puts that into the running config, renames it the running config, and puts it in the regular RAM. So going to 2142 skips that startup file, and that way, the idea behind that is, let's say you get a new job at a company, the old network administrator leaves, and he takes the passwords with him. Or he forgot a password for a router that he hasn't touched in 5 years. But there's a huge configuration on that router. So rather than have to wipe the router and start all over from scratch like you would for a PC, you can actually go in here, you can boot the router up and stop it before it loads the iOS. And then you can change the configuration register to skip the startup file, to skip the configuration file. So then it boots into a blank file. Then you get past the password portion. Then you load the configuration file over, and then you change it. And again, we'll do that in class. All right, so moving on. Your router, what does it do? Your router is like a roundhouse for a railroad. It connects to different networks. It should never have two interfaces on the same network. There are exceptions to this, but as far as this class goes in CCNA, each interface should be part of a different network, just like the roundhouse. So when a packet comes in, the router makes a decision, and he knows that each of these paths go to a different place, but he doesn't know where those places are, how far away they are, things like that. All he knows is when packet A comes in and is destined for network C, put it on interface B, that kind of stuff. So he's kind of like a traffic cop, or a lane changer, if you will. All right, so routers determine the best path to send packets, and what their idea of the best path is, it's all determined by the programming. You can put routing protocols on your routers to make some of these decisions for you, like RIP. RIP will say, okay, there's only one path A has 3 routers in the path, or path B has 2 routers in the path, so I'll go with path B. So it looks for the path with the least amount of routers. Other protocols like EIGRP and OSPF take bandwidth into consideration. So if you've got a path through dial-up and a path through a T1, it'll take the path through the T1. All right, we forward packets out of the egress port. So remember, packets come in through the ingress port and they leave the router or switch through the egress port. All right, so packet forwarding. The old method, I don't even know if anybody still uses this anymore. Each packet, as it comes in, goes to the routing table and is checked to see where it's supposed to go. So even if you have 12 or hundreds of packets coming in that are all going to the same destination, each one gets checked. And again, I don't know if anybody still uses that method. All right, so then we go to fast switching. With fast switching, there's a small cache that stores the last destination information. And as a packet comes through, if the first packet would then have to go check the routing table and make a decision. But then that decision would be stored in the cache, so that the second packet behind him that's going to the same location doesn't have to check with the CPU. So it saves CPU cycles, duh. All right, and then there's Cisco Express Forwarding, CEF. Now what CEF does, it actually builds a forwarding information base, or a fib table. And basically what happens, the fib table kind of solves all the issues ahead of time, and then as packets come in, the fib handles the traffic so that the CPU is left to do other things. So it kind of looks like this. Here's fast switching. So again, there's a small cache. So the first packet that comes in is not for whatever destination's in the cache. So then he's forwarded to the CPU. So the CPU has to make a decision, then he goes out the egress port. But the second, third, fourth, fifth packets that are all going to the same destination, when they hit the cache now has that information, so then they're forwarded out the egress port, and it skips using the CPU altogether. But the problem with this is, let's say the first, second, third packet are all going to the same destination, then the fourth packet's going somewhere different. Well, then the fourth packet would have to go back to the CPU, and that information would be stored here. But then the fifth packet's going to the same place as the first, but now the cache has the information for the fourth packet. But so anyway, it saves time, but it doesn't save as much time as it could, if that helps. Alright, so here's Cisco Express Forwarding. Notice, no matter where the packets are going, the fib table has all their information for them. So there's no need to access the CPU and slow the router down. So as far as routing goes, Cisco Express Forwarding is kind of the way to go. Remember, when your router's sitting there, it's not just forwarding packets. He's talking to the other routers. If you're running EIG or OSPF, like almost every organization is, he's making decisions when links come up, when links go down. Routing tables have to be changed. New neighbors appear, new neighbors go away, or old neighbors go away. So there's a lot of decisions that have to be made by the CPU. So if we can pull just the basic routing decisions off, we free the CPU up to process other things faster. Alright, so the old method process switching is kind of like doing math longhand, each time, even if the next problem is identical. So if somebody gives you 2 + 2 question 4 times, you're going to sit there and figure it out 4 times. Fast switching is like doing math longhand and then remembering the answer for identical problems. And then CEF is like solving every problem ahead of time and putting them in a spreadsheet so that when that problem comes up, you can simply access it without having to do any math. So I hope that helps. Alright, so when we're talking about routers, why do we use the term packets when we're discussing router operation, when we all know that data is sent in a frame? So if frames are sent out the NIC cards to the switch and the router, why does the router call it, why do we always call it packets? Why do routers handle packets? And the answer is, when a router receives a packet, the very first thing he does is he removes the layer 2 header. And once the layer 2 header is removed, it is now called a packet. Remember, when we add the layer 2 header, it's now called a frame. When we remove the layer 2 header, it's called a packet. So with no layer 2 header, the data is called a packet. So again, what happens, packet comes into the router. Router removes the layer 2 frame. Then he looks at the layer 3 information. He makes the routing decision. If there's a path, I'm going to route it out the path. If there's not a path, I'll drop the packet. So assuming he has a path for the packet, he then builds a new layer 2 header and then sends it out. So the layer 2 header is unique to the local network. So in other words, if your router has interface A and interface B, things come in the ingress port of router A, or on interface A, and then they leave on interface B. Those two MAC addresses are going to be on the layer 2 header at those locations. So when packets going from the client to the router, it's going to have the local information for interface A. But after the router processes and sends it out interface B, it's going to have interface B information on there. So the layer 2 information changes at every hop. Again, it's easier for me to show this on the board, so if this doesn't make sense to you or you have a problem understanding this, bring this up when you come into class for your lab day, and I will do this on the board to kind of show you, because this is always like a typical Cisco question too. They show you several routers and they say, hey, here's the information traveling, and here at location 5, what would be the destination MAC of this packet? And you'll have to be able to know that. So remember, the layer 3 information never changes. Layer 2 information is local to the segment that it's on. So the layer 2 information changes at every router. Alright, default gateway, typically called the path of last resort. Some people just call it the gateway. But basically, it's where do I send the frame if I have no idea where to send the frame. Typically, if you have smaller networks that have just one router, so you've got 50 people, those 50 people all go into a switch, and it goes to the stuff, and then it goes to a router, and then it goes out to the internet. Your router is not going to know every path that people type in. Google is an easy one because everybody's Googling. But what happens when somebody types in something weird, like monkeys dancing or something like that? Your router has no idea where those packets go to, where that address is for that web server. So typically what we do is we put in a default gateway on the router. But that's not what we're talking about here. What we're talking about here is each PC needs to have a default gateway, and the default gateway on a PC points to the closest router. And that way, when you type in something silly like funny monkeys or something like that, and your PC's never been there before, he then says, okay, I don't know where to go, so I'm going to send out my path of last resort, my default gateway, and I'm going to go to the closest router. So anytime you're doing a PC or a client's interfaces, the closest port on the router is where his default gateway should point. Typically, it's the very first usable IP address on that network. And in all of our labs, it will be that way. And most of the work world that I've experienced is kind of that way too. Lowest IP address is always the router. However, there are a lot of weird people out there that do it differently. All right, ports on the router. All kinds of different ports, and it all depends. Now here, you can see the bottom portion here. These things are kind of all built in. So here's the router, here's the back of the router. These kind of ports are built in. But then you see these modules that it has. Now typically, you've got ports, or you've got slots for 2 cards. And now here is a serial card with 2 ports. Here is a T1 card with 1 port. So when you get your router, these built-in ports at the bottom are here. These 2 yellow ports are just NIC cards. They're called Fast Ethernet 00 and Fast Ethernet 01. Remember, every port on a router is always numbered from 0 and then up. So the very first port will always be 0. And then you typically have these 2 empty slots, and then you have to buy these cards. And these cards are called WAN interface cards, or WICs. And then, like you'll see, here's a WIC T2 and a WIC 1 DSU, that kind of thing. So they're WAN interface cards. The cards here that you slide in are meant to connect to WAN locations, things across, outside of your network. You got an office 6 miles down the road, or you got some other, you want to connect to the internet, something like that. You can get fiber cards, coax cards, serial cards, T1 cards. They come in a variety of shapes and sizes. Some of them have 1 port, some of them have 2 port. You can even get 4-port switch ports for your router. So those are WAN interface cards, and again, those connect to the WAN. Yellow ports are just NIC cards, and they connect to your LAN. So the yellow ports are your LAN ports, LAN, and then the cards that you add are WAN ports, wide area network ports. Now, then you have 2 other ones. You have got the console and the auxiliary port. So almost every router that you see nowadays has these 4 ports built in, and then you've got 2 empty modules or card slots that you put cards in. So the console port is where you put in your light blue cable to do something locally to the router. When you first buy a router and you get it in, you've got to open it up, you've got to put it on your desk, and you've got to stick a console cable into it, and you've got to give it an IP address. You can't remote into the router until you give it an IP address, and you have to do that through the console cable. So the console cable is what we use in class. Now, there's an auxiliary port. The auxiliary port also works as a console port if you need it. But the original purpose of the auxiliary port, from my understanding, is it was designed for modems. Every router had a modem attached, and that way if you had issues connecting to your remote office or connecting to the internet, you could call Cisco support, and then they would dial in through the modem, access it through the auxiliary port, and then you guys could work on it together. But nowadays we still do that. We still use modems and connect it to our routers, but we typically have those modems turned off, for security purposes. And then if something happens, we can turn them on when we call support, then give them the number. So the console port is always light blue, and it goes to the light blue console cable. Now, Cisco is still shipping these as of today, but all their new stuff has a mini or micro USB on the front or the back, depending on the model. And that's what they're using. Obviously, nowadays, our laptops are not coming with serial ports, so that works. And then the console port, originally built for modems, but it will still work as a console port if somebody breaks your console port for some reason. And when I say breaks your console port, every once in a while something weird will happen where somebody will take an RJ11 jack, a phone jack, and they'll try to jam it into the console port or some other, RJ45 port. And what happens when you put an RJ11 into an RJ45 jack is it bends the pins inside here. Once these pins are bent, it's broke. You can't really fix it without removing it, soldering a new one on. So if that ever happens to you, or for some reason something gets in there and you can't get it out, you can always use the auxiliary port. Now, one thing to remember, when we're dealing with packet tracer in the CCNA, packet tracer at this point does not support the auxiliary port. But on the regular router, you need to remember to turn that to do the security features. So remember, like when we're doing this, the console port, we go into line console 0, enter, password Cisco, enter, login, enter, logging synchronous. So we do those commands. You also need to do line aux 0 and then do the same 4 commands. Password Cisco, login, logging synchronous, exec timeout. What happens, a lot of people, learn Cisco in the labs and stuff, and where we're always using packet tracer, and they forget about the auxiliary port. And then when they go out to the real world, they're never configuring their auxiliary port. So the auxiliary port's wide open. So you don't want to do that. So again, these 2 ports are lines, and then everything else is an interface. So the yellow ones are interfaces, your cards are interfaces. So interfaces get IP addresses, and typically get 3 commands: IP address, description, and no shut. And then lines get 4 commands: password Cisco, login, logging synchronous, and then exec timeout. Alright, moving on. So your basic router configuration, whenever we say put a basic configuration on there, what we're saying is give the device a name, a host name. So it's host name space, JMAC router. So the name cannot contain spaces, but you can do underscores. Your name should identify the model of the router and the location, like Bolivar 2811 or something like that. All right, secure the management access. So basically put put passwords on all the ports, line console 0, line VTY 0 space 4, line aux 0. So put passwords on all of those. Do a password on the privilege mode, so enable secret Cisco, and encrypt all the passwords with service password encryption. So that's securing management access. All right, then configure a banner. You need to have some kind of warning on there so that legally you're covered if somebody hacks into your router and says, "Oh, I didn't know it was so-and-so's router." Something says authorized access only. If you need access to this, please call this number. Again, there's a couple different ideas behind the login banner message of the day. Some people say you should put a contact information to contact if they needed to mess with this. Other people say if you give your company name or a person's name, it gives the bad people outside information that they could use against you later on. So again, I guess it kind of depends on what organization you're doing. It's typically safe to put, call the administrator at, and then put some kind of internal number that's not typically listed. Somebody's not an extension, not like the main phone number and extension, but if somebody has a direct dial line or something like that. All right, and then save the configuration. Remember, any configuration that we're working on is in the running configuration. The running configuration is stored on regular RAM. When the router powers down, all that goes away. So the running configuration is just temporary until power is turned off. So we want to save that to the NV RAM, the non-volatile RAM, that we call the startup configuration. So the command is always copy, run, start. It's always copy from location to location. So copy the running to the start. Copy, run, start. All right, so when we say basic configuration, that's what we're talking about. All right, well, apparently I had all this stuff already marked down. So remember, if you do securing management access is enable password, console password, telnet password, and then an auxiliary password if you have the real router. So when we do the hands-on on the live equipment, you need to do an auxiliary one. And then service password encryption. Remember, service password encryption encrypts passwords in the configuration files that are not encrypted. Line console 0 password Cisco would not be encrypted by default. All right, so remember, we have lines and we have interfaces. There's 3 lines that we deal with. We deal with the console, the telnet, and the auxiliary. Now, today we call it telnet, but back in the old days they called it virtual terminal. So that's why the command for that is line VTY, which is short for virtual terminal. And there are 5 lines, 0 through 4. So line console 0, because there's only one console port. Line aux 0, because there's only one aux port. But line VTY 0 space 4, because there are 5 telnet lines. So 5 people can telnet into the router at the same time. All right, interfaces are used to pass data. So lines are used to control. Interfaces are used for data. So we have fast Ethernet ports, which are the 2 yellow NIC cards in the back. And then we have WIC cards, the modules that are the cards that you add. All right, anytime we do a line, So line console 0, whatever it is, it gets 4 commands. Password Cisco, which puts the password of Cisco on there. Login, which activates the password. Remember, just putting a password on there does not do anything. You have to activate it with login. And then logging synchronous. What logging synchronous does, when new system messages pop up, it moves your command down. So if you're in the middle of typing a big long command and you've got 12 words done already, and then a system message pops up because an interface comes up or down, it does not break up your command, it just kind of moves it down. And then exec timeout 30 space 0 says if you walk away from the router and you quit typing stuff in, it will log you back off in 30 minutes. So the first number is minutes, second number is seconds. And again, there are going to be times when you're working with other locations. It may be a mini mall, and in a mini mall what happens is typically there's a central like wiring closet. So all the store's wiring goes to the central closet, and then every different routers, like they'll put up like a 5-tier shelf, and then every store gets a shelf. So any other IT guy from the other companies all have access to your router. So you don't want to be in there programming, then like somebody comes up, hey, let's go do lunch and come back later, and then leave it in global mode, and then somebody else comes in and plugs a cable in, and he's writing global mode past the passwords. So you want to put an exec timeout. Now for class, we typically use 30 space 0. So exec dash timeout space 30 space 0, and that leaves it out for 30 minutes. And that way, as we're doing our labs and stuff and we're talking, it doesn't log us out. In the real world, you want to make that smaller, typically at least 15 space 0. All right, interfaces. Remember, your interfaces are things that pass data. Your fast Ethernet ports, fast Ethernet 00, fast Ethernet 01, the yellow ports on the back of the card that are built in, or the WAN cards, the WAN interface cards. Now, they typically get 3 commands. That's an IP address, because you got to put an IP address on them so they know where to go. A description, what they're connected to, and then no shut. Remember, all interfaces are shut down by default, so we have to do no shutdown and bring them back up. Now, in class, we're typically dealing with serial cables. One end of the serial cable has to set the clock rate. So it's just clock space rate space, and we use 64000 in class. So the clock rate goes on the DCE end. So our cables have a DCE and a DTE. So the CE end gets the clock rate. So that's how I've always remembered it. If the end has a C in it, it gets the clock rate. So only one end gets the clock rate, and then he specifies how fast those bits, move. Now, back to this description line. Your description, depending on what it connects to, should have a lot of information on there. For example, like whenever you buy a T1, you may buy T1s depending on what company they're going to. Sometimes they're on different provider networks. They all have a T1 circuit ID. They always have different phone numbers to call for service, that kind of thing. So typically in my descriptions, I've always put all the information in there. So as long as I have the router configs and an interface goes down, I know exactly what to do. So as an example, so this would say description, T1 connected to Bolivar, circuit ID number blah 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 blah, AT&T owned for service call blah 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 blah. And that way when the Bolivar interface goes down or for some reason, and I know it's not my routers and I get a call, I got all the information right there with me, because when you call them, first off, digging for these numbers is always a pain in the butt. Second off, finding the circuit IDs and where do I got those listed at kind of be a pain. So having them all on your router helps immensely, especially if you're at home, because then you can just dial into the router and get this information. All right, now we're going to move away from the routers a little bit and talk about IP6. Remember, IPv6, each IP address has 128 bits. The first 64 bits are like the network, and the second 64 bits are the host. So we only route to networks and not IP addresses. So remember, any IP address with all zeros in the host portion is a network ID. Which means in your routing tables for IP6, you're only going to see 64 bits because everything else is host portion. All right, there's also 2 rules that you can use to condense the IP to the IP6 addresses. First, an IP6 address looks like this. So there's 4 numbers, 4 numbers, 4 numbers, 4 numbers, blah blah. Remember, and these are hexadecimal, so they can be 0 through 9, and then A through F. So there's 8 sets. Now remember, the last 4 are for the host portion. First 4 are for the network. Remember, these first 3 are they're called the prefix or the global identifier. This is what's going to be different for you for each person. And then this fourth one is where you subnet. Now we'll get into all that later on, but there's two rules. The first rule is you can eliminate or you can eliminate one group of zeros, and then the second rule is then you can eliminate leading zeros. So here where I've got one, like I'm actually going to turn this into an IP address to assign to an interface. First thing I can do is get rid of these three groups of zeros and replace it with a double colon. And then I get rid of leading zeros. So the zero here in front of it goes away. These three zeros go away, so just one. And then these three zeros go away, so it's just one. So this whole big address can be abbreviated to this. Now again, this is just a refresher. We'll get into this more in class if you have not covered this in your intro networking class, which you should have. All right, first IP6 is at this point is not turned on automatically on your router like IP4 is. So to turn it on, you want to do IPv6 unicast routing. And then to do an IP address, everything's the same except you put the v6 in front of IP. So on an IP version 4, it's IP space address space blah 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 blah. And then if you're going to put an IPv6 address, it's IPv6 space address. So everything with IPv6 is separate from IPv4. There's IPv4 commands and there's IPv6 commands. Typically the only difference is adding the v6. So IPv6 space address space, and then you put the address /64. Now we typically, with IPv6, we never write out the subnet mask. It's almost always in slash notation. Most of the time it's 64, but again, it all depends on how many bits you use. So the /64 says I'm using all 64 bits here for the network portion of the address. All right, loopback interfaces. Loopback interfaces are virtual interfaces that do respond to traffic. And they have all kinds of purposes. One, testing, pre-configuring a network before hardware arrives. So basically, let's say you've got a big complicated network and at the end of it you're going to add a new office and you're waiting for the new router to come in, or you're waiting to get the T1 turned on and you've got to wait a week. So what you can do is go to that router and you can create a loopback interface that's going to have the same IP address of that remote router. And then you can set up all the stuff on your internal network first, and then the loopback information will respond to pings and things like that. And that way when the T1 gets turned on, all you have to do is just eliminate the loopback and then turn on the interface and you're all set because you've done all your programming ahead of time. Other things like EIGRP use the loopback interface for election processes to determine who's going to be what. So as far as at this point, all I want you to know about loopback interfaces are they're virtual interfaces. You can create as many as you want, and they do respond to traffic. So I can have loopback 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, that kind of thing. And again, we use them for testing. Alright, so to create a loopback, you just go to global mode, so config T, then interface loopback 1, enter, IP space address space 192.168.1.1, enter. And loopback interfaces come up automatically. You do not have to do a no shut on loopback, but if you do, it doesn't hurt anything. Alright, so normally in class we do a walkthrough of this. Again, when you guys come into your lab day, we'll do this walkthrough. All right. So once you have your interfaces set up, you want to verify your interfaces. The fastest way is show IP interface brief. And if you're doing IP6, it's show IPv6 interface brief. So when you do show IP interface brief, it shows you every interface on the router, whether it has an IP address assigned or not, and then the status and the protocol. Now status only tells you one thing. Is the interface turned on? Remember, we turned it on with no shutdown, or no shut to abbreviate it. So if the status is up or the status is down, you did the no shutdown. If the status says administratively down, you did not do the no shutdown. So you need to go back to that interface and turn it back on. Now, protocol tells you whether it's connected to something on the other end. Is it seeing the other end active? So you can be down and down, which means that you've done no shutdown, it has an IP address, but you're not seeing something on the other end. For some reason, your router's not communicating across. For some reason, either the other end is down, your configuration's wrong, something like that. Alright, so show IPv6 interface brief will show you typically two addresses. There's always a link local address and then the IPv6 address that you assign. Now remember, FE80 is a link local address, which means it's like the private IP address for IPv6. So remember, in IP version 4, we have 3 private IP addresses, 10, 172.16, and 192.168. So everybody's home is 192.168, and then they have a public IP address. So your routers with IPv6 can have 2 addresses, a link local address, and then an address that you assign on there yourself. So when you see 2 addresses, don't let that freak you out. Alright, if you do show IP route, it'll show you the routing table, or show IPv6 route to see the routing table for IP6. So remember, with the routing table, and again, we'll have a chapter on routing tables, but just a brief overview, it shows you, these are the networks that my router knows about. The letter over here shows you how the router learned about those networks. So R, if I go up to the table, R, I learned about it through RIP. So this router has RIP running. And then C is directly connected. So this router has 3 connected networks, and then he knows about 5 remote networks through RIP. So these are the networks he knows about. This really kind of tells you how he learned about them. So with RIP, the administrative distance is 120. We'll get into all that. But the rest of this says, in order to get to this network, this is the target that I sent to. This is the next hop, the next step. This is how long I've known about the route, and this is my exit interface. So each route typically has an IP address for the network ID. Here's the network I know about. Here's where I send to the target that I send to next, and then here's my exit interface. And then if it's directly connected, hey, this interface is directly connected on the fast Ethernet 00. And again, we have a whole chapter on the routing table, so don't get too caught up into that yet. Alright, so when you're doing your show commands, show run, show whatever, there's the pipe command that we need to talk about. So the pipe command is the command right below backspace, and on the keyboard it kind of shows you, it's got like a little dash in the middle of it, or an empty space, but it's typically represented as a pipe or a line going down. So don't let that key throw you off. So it's the key right between backspace and enter, it's the backslash, and then if you shift, it's a shift. If you shift that key, it's a pipe. And you can use the shift key to filter through the commands. Remember, in our labs we typically have small 2 or 3 page configuration files. But imagine how big the configuration files are at Time Warner Cable. So you need to be able to filter to get to what you want. So I can do show IP route to show the routing table / begin gateway, and that will skip the legend at the top. Or I could show IP interface brief space include up to only show me the operational interfaces. So things like that. So the pipe command does that. And after the pipe you can do section, so section EIGRP, or include up interfaces, or exclude down, or begin at interfaces. So these 3 words can follow that, so begin, include, that kind of stuff. So it's great for filtering your commands. You will probably forget about this, and then someday you'll be like, "Whoa, why didn't we cover it in class?" Well, just so you know, we did cover the pipe command. Alright, your command history. Remember, by default, the last 10 commands you entered in that mode are recorded in the history buffer. And you can use the up arrow or the down arrow or Control P and Control N. To cycle through those last 10 commands. And that way when you're doing your lines, line console 0, password Cisco, you can do up arrow when you do the next one. So then I go to line VTY04, enter, up arrow a few times, enter, and that way I don't have to keep typing the same commands over and over again. You can change this to make it bigger, and the command is terminal history size, and then however many commands you want to remember. So if I wanted to remember 100 commands, terminal history size 100. Now, I personally have never changed this myself. Typically, my 10 commands are good for me, but it all depends. Now, if you want to see the last 10 commands that are entered, you can do show history, and it'll show you the history of the last commands that you entered. Remember, in that mode, once you change modes, typically the buffer clears. Alright, load balancing. There are 2 forms of load balancing. The first one is equal cost load balancing. All routing protocols will do equal cost load balancing. What equal cost load balancing is if there's 2 paths to a destination and they both have the same cost, I'll use them both. So I'll split this information. So the first packet will go to route 1, second packet will go to route 2, third packet will go back to route 1, route 2, that kind of stuff. So there's an equal cost, there's a balance. So all routing protocols can do that. Now, unequal cost load balancing, there are 2 ways to get there, but they're not equal. I may have dial-up for path 1, but then I've got fiber for path 2. So naturally I want to use the fiber. But with EIGRP, I can actually use both. So I'll send let's say 50 packets through the fiber and then 1 packet through the dial-up. So I'm doing unequal cost load balancing to get all the packets there as fast as possible. And it calculates this so it knows how much data to send on which route at what times, that kind of thing. So at this point, only EIGRP supports unequal cost load balancing. All right, administrative distance. When 3 people tell you something, but all their stories are different, which one do you believe? And it's the one that you trust the most. So with routing protocols, because there are different routing protocols, and your router can learn about a route different ways. If he's directly connected, he knows about a route. If you put it in manually, it's a static route, then he knows about that manually. If it's running EIGRP or OSPF, that kind of thing. So because your router can learn about things from different sources, Cisco has put like a trust level on each source. So the lower the trust level, or the lower the administrative distance, the better that route is, the better the trustworthiness of that route is. So a directly connected route always has an administrative distance of 0, meaning directly connected route is always used before anything else. So if I've got EIGRP telling me, oh, to get to the network, go there, or if I have a directly connected route, I'll always take directly connected over anything else. All right, and then static routes. Static routes are routes that you've entered manually. So Cisco assumes that if you've entered it manually, you want it to take precedence over anything else. So static routes have number 1. All right, now there's 3 other ones you need to learn for the class, and that's EIGRP. EIGRP is 90. Now they call it internal EIGRP, and we'll talk about all that a little bit later, because you can use EIGRP internally on your network, you can use EIGRP externally on the internet, but when we say EIGRP, we're talking about internal EIGRP. So for the CCNA, make sure you know that EIGRP has an administrative distance of 90. All right, then OSPF has an administrative distance of 110, and then RIP 120. So those are the 5 you have to know by heart. So RIP is 120, OSPF is 110, EIGRP is 90, static is 1, and connected is 0. And that way, when you see something like it'll show you a routing table that says, hey, I've got 2 paths. I learned 1 through OSPF and I learned 1 through EIGRP. Which path will I select? Well, I'll select EIGRP because his number is lower than OSPF. Hey, I got 2 of them that I learned, OSPF and RIP. Which one do I pick? Well, I pick OSPF because it's lower number. Hey, I got 2 paths, OSPF and static. Which one do I pick? I pick static because he has the lowest number. So lowest number is trusted the most. All right, so remember, your router only learns routes in 3 ways. The network is directly connected. So when you first turn on your router, he boots up and then he says, hey, I got 2 interfaces that are operational. They connect to network A and network B. So those are directly connected networks. And that's all your router knows about automatically. So at that point, then you need to put in routes as a user. So when you manually put in a route, that's called a static route. And then if you wanted your router to learn routes automatically, you can install RIP or EIGRP or OSPF, and those are called dynamic routes. So those are the only 3 ways you can learn about routes. Directly connected when your router first boots up, manually because you put them in yourself, or from a routing protocol. So again, how do we learn about the routes? They'll show up here in the routing table. So show IP route shows me that RIP is running on this router, and then it's got some directly connected networks. Now remember, we talked about that administrative distance. With RIP, the administrative distance is 120. So that's why this 120 is there. It's the administrative distance. All right, so again, when you look at these routing tables, they show you, how did I learn about the route? So the letter shows you how I learned about the route. Now what will happen is you'll get something like this on the CCNA. Now obviously they'll cut this piece off the legend here. So they'll just show you this. And they'll say, hey, what routing protocols are active on this router? Now they may show you the letter, they may not. But obviously in this case, there's only RIP that's running. If they cut the letters off, they expect you to be able to go here to this column and see that 120 is RIP, and then this router is running RIP. So that's why you have to memorize the 90, the 110, and the 120, so that when you look at a routing table without the letters and without the legend, you can identify how these routes were learned. All right, so remember, first one is how the route was learned. This is the target network. So I know about this network out there. Somewhere out there, there's 192.168.8.0/24. And then I've learned about the route through RIP, and then I know that there's two routers between me and the location. So I learned about it through RIP, and there's 2 hops. It's 2 hops away. All right, and then via, where do I send to? And then here's the target IP. So in order to get to here, I don't know where this is, but I know it's 2 routers away, and the next router is at 192.168.5.2. How long I've known about this route, and then this is my exit hole. This is the hole I'm going to send my data out of. So it's going to go out serial 0. So it's going to have serial 0's MAC address as the source, because remember, the layer 2 information gets changed. And it's going to be destined for this IP address. So that's my egress, or this is my egress port, and that's my target IP address that I'm sending to. All right, so your turn. If you've got this shown up in your routing table, what's the address of the remote network? What's the address of the next hop? And how did this router learn about this route? All right, so address of the remote network is right here, 192.168.4.0. Address of the next hop is here, and I learned about it through RIP because this says 120. All right, so just a couple of brief points about your routing table. The routing table is just a list of the networks that your router knows about. And one router's routing table may not have the same information as another router. So your routing tables between routers can be different. And another thing, routes are always one way. So just because you're a good boy and you put in all your routes and you can point to the remote network doesn't mean that the remote network can get back to you. So remember, all routes are one way only. So in order to make a route there and back, you need to make 2 routes, one there, one back. And then routes are one hop only or next hop only, meaning your router may know about the remote network out there. So hey, the remote network's out there somewhere, and it's 3 hops away. I have no idea what those 3 hops are. I only know the next hop, the next link in the chain. So that's kind of how our routers work, kind of on a next hop basis. If I know to get to A, and A knows to get to B, and B knows to get to C, and then C is directly connected to D, I can get there. So that's kind of how they all work. All right, static routes. Static routes are routes that you enter manually. And again, they're one way. All routes are one way. They do not update when a change occurs automatically. And this is the problem with static routes. When something changes, you have to go back and modify all the routes. Well, I'm sorry, delete and recreate. Because they cannot be modified. They must be deleted and recreated. And your static routes can end in 2 ways. You can either end it with the next hop IP address, or you can end it with your egress port. So here's 2 examples. It's always so you go into global mode, then IP space route space the network I'm trying to get to. I'm trying to get to 192.168.1.0, and then his subnet mask is 255.255.255.0 space. But in order to get there, I need to send to 10.1.1.1. Or, same thing, IP route, blah, 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 space, I need to exit out FA00. Now, one of these is preferred over the other, and the reason is what they call a recursive lookup. And what they're saying is a recursive lookup means if I put a destination IP address like this, it causes 2 router lookups. So basically, if I put in this top static route, so a packet comes in destined for 192.168, 1.500, or well, it's the 1.200. So packet comes in. So I go through the routing table, then I find this route. Hey, 192.168.1.0, I got to send to 10.1.1.1. Well, then now I got to figure out where 10.1.1.1 is. So then I got to go back to the routing table and find a path for 10.1.1.1. So I do 2 lookups in order to get to that one packet's destination. So that's called a recursive lookup. If I do the second route, IP route space blah blah blah, I know, oh, in order to get to here, I send out this hole. So everything's done there for me. So I only have to do 1 lookup. So again, recursive lookups are typically, we want to avoid that. So we typically want to end static routes with a egress port, or our port number that we our exit port, if that helps. All right, default static route. default static routes, sometimes called quad zeros. And this is where it's kind of like a default gateway for routers that we talked about earlier. So if you've only got one router and he points out to the internet for all your stuff, you got 50 users, you got an email server, you got all your stuff here, and then you go out to the router, then the router goes out to the internet. Excuse me. So in that case, I can make this default static route, IP route 0000, which means everything matches, and then forward it out to my ISP's IP address. And what this says is, anytime a packet comes in and it doesn't match the stuff in my routing table, this route will be at the bottom and we'll catch it, and then we'll forward it out to the ISP so that the ISP can figure it out. So you got that one weird user, and he's into like monkeys eating, ticks off other monkeys. So he types in something weird. His PC has no idea where it is because it's never been there. So his PC forwards out his default gateway and then goes to the router. The router gets in, it's like, holy crap, what's this guy smoking here? But doesn't tell him that. But then it goes to the routing table, and he has no idea where to route this to. So then the quad zero says, hey, you don't even have to match, and you match me. And then it'll forward out to the ISP. The ISP will get in, he was like, hey, I don't know what kind of freak looks at this stuff, but I don't have an address for this either. So then he'll go to the .com server, because your ISPs default to the .com servers. And then the .com servers say, oh, I know where that is. Some freak created it here. And then he gives me the IP address there to the ISP. The ISP gives it back to your router. The router gives it back to the PC. And then the PC uses the IP address to get there. So it's kind of like a default gateway for routers. So it's used to forward, and again, it's typically called the quad zero. All right. When we talk about routing protocols, there are several routing protocols, but the three we're going to cover are RIP, OSPF, and EIGRP. Now, RIP isn't really used anymore. But it's still supported by everything. So sometimes you can use it in a pinch. Like there were times when I was waiting on a piece of equipment or something like that, so I just took a PC and put Microsoft Server on there and stuck a second NIC card in there and turned on routing and remote, or what was it called? Routing remote access, something like that. And it supported RIP, and I could turn this PC into a router temporarily to do stuff until the regular router came in. So it kind of works in a pinch. So with IP4, we talk about RIP, OSPF, and EIGRP. So RIP was the first one, open source, the oldest routing protocol. And then there's OSPF and EIGRP. OSPF is open sourced, and then EIGRP is a Cisco proprietary. So EIGRP is Cisco's baby, and then OSPF is open source. There's also ISIS. We don't talk about that in CCNA. Then over here at IP6, there's RIP Next Generation that supports IPv6. There's OSPF version 3, and then EIGRP. So those are the three routing protocols that eventually we'll get into. Now, in this class, this Phase 2 class, we're only going to talk about RIP for a little bit, and then we're going to get into OSPF. Then if you go into Cisco Phase 3, we get into EIGRP. All right, so that kind of wraps it up. Let's see what's in your Angel folder real quick. All right, this week you've got some basic IPv6 configuration PDF. Wait for it. Keep waiting. And again, this comes from Cisco. It has really all Cisco's information on basic IPv6 kind of stuff. And then if we go back to week 5, wait for it. And assignments. There's your assignment. So again, there's the quiz. Remember the assessments on the Academy website. You may have a pop quiz when you come in for your lab day. And then there's your assignments that are due. All right, well, hope that helps. Again, if you have questions, make sure you bring them to class. So remember, you should be reading the textbook, watching the presentation, and then you should be writing down questions at both times. And then when you come to the lab, you should be asking those questions. Remember, when you graduate from college, everybody's going to have the same degree that you have. But they're going to expect you to know this material. So when they interview you, they're going to be asking you technical questions. When you get hired, they're going to expect you to be able to do some of the stuff. So if you screw around in class and you kind of get a D and you skate by, you're going to have a problem getting through the interview process. And even if you do manage to get lucky enough to get interviewed and actually get in, you're not going to be able to do the job. So you're paying for the class. Make sure that you're actually using this material and you're actually getting your money's worth. All right, guys. See you in class.